Welcome to the first lecture of the Skill Up, Skill Down module of this massive open online course. Scaling up and down are key activities in the process industry and equally apply to chemical processes, polymer processes and fermentation processes. We will discuss what happens if processes go bigger or smaller. This is of course a course on conceptual skills. It is not teaching of thermodynamics, transport phenomena, reaction kinetics and so on, but some basic knowledge on these topics will be needed. Small skills should be understood as everything that you typically do in a lab environment, up to the scale of a few liters, including the milli and nano skills for specific tasks like high throughput screening and catalyst improvement. Large scale is the final skill at which commercial processes are operated. The basic approach that we will advocate is the following. Scale up is key for commercial success, but can only be done properly via scale down. So first you analyze the commercial scale, and then you mimic the essential characteristics of the large-scale process in the lab, in a scale down model, and you do the optimization there where it can be done fastest, cheapest, and with the lowest risk. Only then one designs or optimizes the commercial process, and this means that scale up starts at the commercial scale. Leo Berkeland, a famous chemical engineer and inventor of bakelite, the first plastic, summarized it well 1 century ago by stating, "Commit your blunders on a small scale and make your profits on the large scale." This lesson has been successfully brought in practice in the field of process engineering with numerous products. Why are industrial processes big? Well, investment costs scale with the equipment area. Basically, you buy equipment walls as steel or concrete. Also, operation costs often scale with heat losses, which is related to the area. Capacity, however, scales with volume. So we see that upon scale up, the total costs go down with a capacity to the power 2/3. In practice, depending on the specific equipment, this factor is between 0.5 and 0.9. This phenomenon is commonly known as the economy of scale. In biology, something similar has been found. Already in the 1930s, Kleiber found out that the metabolic capacity of species scales with the body weight to the power 3/4. Like in processes, also in animals, the heat transfer by sweating and sometimes the mass transfer, oxygen supply and CO2 ventilation through the skin of insects appears to be optimized in concordance with the ratio of area over volume. Scale up comes with risks. Very often, there are scale effects and the performance of a process changes with scale, where it is usually lower on the large scale. Dealing with these risks has resulted in 2 main strategies applied in industry, either innovative or conservative. The innovative one is increasing in size to capture the economy of scale, with examples as stir tanks, power plants, airplanes and bridges. The conservative approach is increasing in numbers. This means copying large numbers of smaller equipment to achieve the required volume. This strategy is of course less risky, but often more capital intensive. Examples are membrane reactors, compressors, solar panels, and computer clusters. Zooming in on scale-up losses in large vessels, it appears to be impossible to scale all the relevant factors of a process in the same way. Because of the larger distances and the limited area per volume, the rates of mass transfer, heat transfer, and mixing will become relatively slow, while at the same time the reaction is not directly affected. A microorganism doesn't know whether it's in a small or a larger tank. Transport limitations will then result in reduced rates and difficulties to control temperature, concentrations of slowly added substrates like carbon sources, oxygen, and toxic byproducts such as CO2. This is the reason why we advocate scale down, to first analyze the large scale and then mimic the rate determining steps on the smaller scale. This might very well bring a lower performance than in the ideal lab scale process, but trying to bring an optimized lab process to the factory, that is a recipe for failure and disappointment. Let's now try to analyze this in more detail. Assume a process converting cheap feedstock into higher value products. Inputs to the process are material, thermal energy and momentum, for example liquid motion by a rotating impeller. Whereas outputs are converted materials, higher thermal energy due to exothermic reactions, and there's less momentum, mostly dissipated into heat. There is a skill effect in a larger vessel. When in a larger vessel, the same relative inputs result in different outputs, which are usually lower. This means that the volume-specific balances are different. The laws of physics dictate that the balance reads accumulation equals reaction plus transport. Reaction kinetics are skill independent when concentrations, temperature, pressure, pH, the catalyst concentration, and the maximum reaction rate are the same at different skills. But scaling issues on the reaction side can arise due to skill effects on the wall area per volume and fluid velocities. Surface area related mechanisms such as adsorption, leaching and diffusion limitation can limit the conversion kinetics. Further, liquid velocities are different, which can affect mixing or the local concentration of catalyst due to settling or washout. Transport mechanisms nearly always depend on skill, because they depend on area like cooling or CO2 transport, where area per volume decreases with size. For a 1000 times larger vessel, there's about 10 times less area per volume. Skill effects can be minimized by taking the following 5 precautions. Correctly judge the mechanisms. For example, disappearance of a chemical species can be either due to conversion or transport, which should be understood. Avoid skill effects, skill-dependent factors that influence conversion related to wall kinetic effects, diffusion limitation, and local concentration of catalyst particles. Try to maintain at least the same transport mechanisms by keeping the same flow pattern at different skills, using, for example, special distributors, guiding surfaces, or packings. Avoid new transport mechanisms upon changing skill, such as vortex shedding, cavitation, and turbulence. And keep the same velocities where possible, because in multi-phase systems, changes in velocity affect the dispersed phase. Think of particle size, washout, and settling. Because not all transport mechanisms and rates can be kept the same across the skills, we conclude in general that skill problems are transport problems. Ideally then, all resulting volume-specific balances should be skill independent. This is the basis of the powerful concept of similarity, and we will dive deeper into this in the next lecture.